Hey everyone. So in this video, we're going to go over a light review of transformations. And so now that we've graphed y is equal to sine of x and y is equal to cosine of x, we're going to start looking at graphing slight variations of these functions. So one example of a function that I'd like us to be able to graph by the end of our discussion of transformations of sine and cosine is something of the form y is equal to negative 3 times sine of pi over 2 times x plus 1. So this is just one example of an equation I'd like you to be able to graph without too much difficulty in the near future. So this is not something we're going to cover in this video. We're not going to spend any time in this video going over sine and cosine, but we're just going to talk about transformations in general. And so, when we graphed sine and cosine, we just plotted a bunch of different points and sketched the curve that ran through all of these points. And of course, plotting points to graph an equation always works, but there's a lot of patterns when it comes to graphing equations, and really we want to take advantage of these patterns to graph new functions using our understanding of old functions. And so this is the idea of transformations. And so really what we're going to do in this video is that we're going to look at different ways we can change an equation, and we're going to look at how those changes influence the graph of that equation. And so what we're really going to do is we're going to start sort of working through and filling out this table that I have here, sort of one box at a time. So let's take a look at this function f of x is equal to the absolute value of x. So I've graphed this function on the right, and what I want to do is I want to explore this function g of x is equal to the absolute value of x plus 3. Now, this is really the function obtained by taking my f of x function and just adding 3 onto the end of it. This is really just f of x plus 3. And so f of x, this is giving us the outputs of the absolute value function. Right, if I plug in 2 into the absolute value of x, I'm going to get 2 out. And so the point 2 comma 2 is on the graph of our f of x function. Well, the analogous point we see on our g of x function is the point 2 comma 5. If I plug in 2 into my g of x function, I'm going to get, well, the same result, but then 3 more than that. Right? So I'm going to get 5 out. The absolute value of 2 plus 3 is going to give me 5. And really that's going to happen no matter what number I plug in for my g of x function. I'm just increasing my result by 3, and so really all of our outputs, all of our y values are going to increase by 3. The points are all just going to shift up 3 units. So this is going to happen really for every point, and really our graph of our g of x function is going to look something like this. It's going to be the graph of our original function shifted up 3 units. So this is g of x is equal to the absolute value of x plus 3. Now what about if we look at the function h of x is equal to the absolute value of x, let's say minus 2. Right, so it's our f of x function, but instead of adding 3, we're subtracting 2 this time. Right, so this can be seen as f of x minus 2. Well, the same thing is going to happen, except we're just going to shift our graph down 2 units. Right, so here I can kind of see my h of x function really as this one here. So this is h of x is equal to the absolute value of x take away 2. And so in general, if we're going to add some number onto the end of our function or subtract a number onto the end of our function, what this really does is just shift the graph of our function up or down that many units. So let's write this idea down in our table. So the idea is that when we take our function f of x and we add some constant to it, this is going to amount to a shift in the vertical direction, up or down. And when c is greater than 0, we saw that, like when we added 3 onto our absolute value function, we saw that this shifted our graph upwards c units. And when we saw that we subtracted 2 away from our function, our graph shifted down 2 units. So when c is less than 0, we're going to shift the downwards direction. So now let's take a look at this function f of x is equal to x squared, which I've graphed on the right here. So what I really want to explore is this function g of x is equal to, in parentheses, x minus 4 squared. So how does this function, the equation of this function, compare to our original function f of x? Well, really g is the same as taking f and replacing its input with x minus 4. Right, they're both square functions, one is just squaring x, the other one's squaring x minus 4. And so how does this change the graph of our f function when we subtract away 4 from the input? You know, earlier we saw that when we subtracted or added a number to the output of our function, this amounted to a vertical shift. Well, when we add or subtract a number to the input of our function, that's just going to amount to a horizontal shift. And so, you know, the question is this going to shift the graph left or right? And maybe we can reason through this for a moment. You know, here what we're really doing with this g of x function is it's squaring something. And whenever we square a quantity, well, we're never going to get a negative result from squaring, right? Any number multiplied to itself is going to be non-negative. So we're not going to get any negative results from this g function. But when are we going to get the lowest possible value from this g function? Well, the lowest value we can get, if we can't get a negative value, the lowest value we can get is 0. And that happens when x is equal to 4. Right? When x is equal to 4 here, we're going to get 4 minus 4, that's 0, and 0 squared is 0. So really what we're saying here is that the lowest possible point on this graph of this g of x function is going to happen at the point 4. At the x value of 4, we're going to get an output of 0. And so this is suggesting here, if really this g of x was just going to be a shift left or right of this function, this is suggesting that g of x subtracting away 4 from our input is going to shift our graph right 4 units. And that's true. And so here, you know, I would encourage you to pause the video and plug in other values to really convince yourself that we'll get a shift right 4 units, but this is going to be the graph of our g of x function. This is g of x is equal to x minus 4 squared. And so we can see here that this point, for example, 1, 1, that got shifted 4 units to the right by this subtraction of 4. Feels a little bit backwards, and that's kind of the case with adjusting or applying transformations to the input of our function. So it sort of works in reverse. But when we subtract 4 from the input, we're going to shift our graph 4 units to the right. And so hopefully that suggests to you what happens when we take h of x is equal to x plus 3 squared. So what happens when we take our input and we add on 3 to it, right? So h of x is really just f of x plus 3. It's replacing x with x plus 3. Well, this is going to shift our graph 3 units to the left, right? So if we go through the same logic, you know, we know that we're going to get only non-negative values from this square function. And then we can just ask, when do we get that lowest value, that value of 0 from the square function? Well, that happens when x is negative 3. Right? So here I know that really our h of x function, you know, looks like the same function, just shifted to the left 3 units. And so here this is h of x is equal to x plus 3 squared. And if you feel unconvinced, really I would encourage you to make a table for these two functions and really see that these are the cases. But really the main takeaway here is that when we add or subtract to the input of our function, we're going to shift our graph left or right. And in some sense, it's probably the opposite of what you might expect it to be. And so let's go ahead and write down this idea in our table. So if we take f of x plus c, where that addition of c is inside the input, well, then we're going to have we're going to have a horizontal shift left or right. And when c is less than 0, when we're subtracting from our input, that's going to amount to a shift right. And when we're adding to our input, this is going to amount to a shift left. So let's do the same thing, but instead for this function, g of x is equal to negative x squared. So here I'm taking my f function, f of x is equal to x squared, but I'm just going to negate the function itself, right? This is really just taking our original function x squared and incorporating and just negating the entire function. So this is negative f of x. So what do you guess would happen when we negate this entire function? What happens to the graph of this function? I would encourage you to pause for a moment and think. But what's going to happen is that our entire graph is going to be reflected over the x-axis. Really, we're going to take the picture we have here on the right, and we're going to reflect it over this horizontal axis. Right? The idea is that, here, if I take, if I look at this particular point, 2, 4, right, that's saying when I plug in 2 for x, I square it, I get 4. Well, in g of x, it would do one more step and negate that result and give me negative 4. It would give me a corresponding point down here. And that would be the same for all of the points. It would just negate our output values and bring them across the x-axis onto, here in this case, all the negative values. And so here we would end up with this graph here. So we'd have the point 0, 0, negative 1, negative 1, negative 2, negative 4, 1, negative 1, and we already saw 2, negative 4. So what happened when we took our function and we negated it? Well, this amounted to a vertical reflection over the x-axis, the horizontal axis, right? So we took our horizontal axis and we reflected vertically over this axis. So what if instead of negating our entire function or the outputs of our function, we negated the input? And so let's say we had the function g of x is equal to the square root of negative x, which, this would be obtained by taking our f function and replacing x with negative x, right? Negating the input of our function. How does this change the graph of f? How does this change the graph of our function? Here, let's make a small table just to really see for ourselves what happens. Right, so the square root of x doesn't take in negative numbers because the square root of a negative number is undefined or not a real number, or not a real valued number. And so here, if I want to make sure we're taking the square root of a positive number, I actually need to plug in negative numbers because of that extra negative sign underneath the square root. If I plug in 0, negative 1, negative 4, and negative 9, what we get is the square root of, well, negative 0 is still 0. The square root of negative 1 is, well, actually we're not taking the square root of negative 1, we're taking the square root of negative 1. This is the square root of positive 1. We've got the square root of negative 4, and the square root of negative 9, really giving us square roots of 1, the square root of 4, and the square root of 9. 1, 2, and 3, respectively. And so the graph of our function, g of x, is really just going to have the same values as our f of x function, but they're going to be reflected over this y-axis, right? To get the same values, the same outputs that we got for our original function, I had to plug in the same x values, but just their negatives. And so if we take our function and we negate the input as opposed to the output, this is going to give us a horizontal reflection of our graph over the y-axis. Right, so here I'm going to have my y-axis, and really negating our input is going to reflect our graph over this vertical axis. It's going to give us a horizontal reflection. So far we've looked at what happens when we add or subtract to the input of our function, to the output of our function. We've looked at what happens to the graph of our function when we negate the input and when we negate the output. But one thing we haven't talked about is what happens when we multiply some quantity to our input or to our output. So let's start with looking at what happens when we multiply to our outputs. So when we multiply to the function itself, f of x. And so let's start by making a table. So I've already made a table for this function. I'm not giving you the equation in this example, I'm just giving you the table and the graph. And so I want to make a table for 2 times our function, 2 times f of x. Well, f of x is really just giving us the outputs of our function, right? So here, on our left side table, we see the outputs here, 3, 0, negative 1, 0, and 3. And so all we're doing here is we're just doubling these outputs. Right? So here when I plug in negative 1, this is just saying 2 times my output corresponding to negative 1. This is 2 times 3, where it's 6. Similarly here, my output when I plug in 0 is, well, the output of our f function is just 0, and twice that is still 0. If I double my output at 1, well, I'm going to get negative 2. If I double my output at 2, I'm just going to get 0, and if I double my output at 3, I'm going to get 6. And so really, the graph of this 2 times our f of x function, it's just going to take all of the outputs of our function and stretch them by a factor of 2, right? It's just multiplying all the outputs by 2, and that really means taking the outputs and stretching them twice as far away from our horizontal axis. Right? We can see that, if we sort of plot the points on our 2 times f of x function, well, we get the point negative 1 comma 6. We still get 0 comma 0 because 2 times that output, it's not going to change. It's not going to get it stretched any further away from the x-axis because it's on the x-axis. But here, this point at 1 comma negative 1, it's going to get stretched twice as far away from the x-axis. It's going to get pulled down to 1 comma negative 2. And then 2 comma 0, that's going to stay in the same spot. And 3 comma 3, well, the output's going to get doubled to 3 comma 6. And so the graph of this function, is stretched by a factor of 2 everywhere away from this horizontal axis. So we get a vertical stretch by a factor of 2. And so values below the x-axis are going to get pulled further away, and values above the x-axis are also going to get pulled further away. And values at the x-axis, points at the x-axis, are just going to stay stationary. And so maybe we won't go through the exact same motions for multiplying by 1/2, but maybe you can guess here that if we multiply by 1/2 to our function, everything would just get squished down. All of our outputs would get multiplied by a factor of 2, and we would end up with a graph that maybe looks something like this. And so here it might look something like this. If we took 1/2 times our function. And so here, if we take our function f of x and we multiply by some constant, well, this is going to amount to a vertical stretch or compression, as we saw in the previous example. And so here, when we multiply by some number that was greater than 1, well, it's going to take all of the y values and multiply them by something greater than 1, and that's going to make them larger. So this is going to be a vertical stretch if our constant is greater than 1, and it's going to be a vertical compression if our constant is somewhere between 0 and 1, right? If it's negative, we're going to see a reflection, but then the same ideas are going to apply. So if it's some number between 0 and 1, this is going to be a vertical compression. Okay, so what happens now if we take our function and we multiply the input by some number? So here, let's start with this function f of x is equal to x squared. I've got the graph of this function, I've got a table for this function, and I want to look at g of x is equal to, 1/2 x squared. In other words, the function obtained by replacing x with 1/2 x in our f function. So let's again explore this example by making a table. So here, this is a table for f of 1/2 x. So this is 1/2 x squared. Well, if I plug in 0 into this function, 0 times 1/2 is 0, and then squaring that is still 0. If I plug in 1, well, we're going to get 1 times 1/2 squared. That's going to be 1/4. If I plug in 2, we're going to get, 1/2 times 2 squared is going to be, 1/2 times 2 is 1 squared. That's just 1. And then we can see that if I plug in, maybe I'll extend this table, we'll get if I plug in 4, well, that's going to be 1/2 times 4 squared is 2 squared. That gives us 4. Maybe if I plug in 6, we'll see that we'll get 3 squared, which is going to give us 9. And maybe I'll leave it at that for filling out the table here. But hopefully you can see that really, we're squaring numbers here. But to really square the same numbers as we see in our previous function, we have to plug in twice as large of a value. Right, so in our original function, if I plug in 1 and I square it, I get 1. Here I needed to plug in twice as large of a value to be squaring 1. I need to plug in 2. Because of this factor of 1/2, I needed to plug in twice as big of a number to get the same result. And so that's really telling us that I need to plug in numbers that are further out along this x-axis to really get the same heights on my x-axis, the same output values on my, sorry, not my x-axis, the same output values. So here what that's really saying is that the graph of this function, I have my 0, 0, but I'll need to plug in 2 to get the same output of 1. I'll need to plug in 4 to get the same output of 4 here. Really, I need to plug in twice as large of a value, an x value, to get my same outputs here. And we would see that on the negative side as well. Oops, sorry, not there, that would be out here. And so the graph of our function will look something like this. And again, this transformation of our input, multiplying our input by this constant, it kind of did the reverse of what we expected, like when we added or subtracted to the input of our function. Here, multiplying by this factor of 1/2 didn't shrink our graph horizontally, it actually stretched our graph horizontally. And so maybe I won't go through the same thing for this h of x function is equal to 2x squared, but really I just want to say here that this is going to compress our function by a factor of 2. This is going to compress, maybe I should say by a factor of 1/2. So it's going to give us a horizontal compression by a factor of 1/2 when we multiply the input by this number greater than 1, when we multiply by 2. And this multiplication by 1/2 actually stretched our graph horizontally. And so in general, if I take f of c times x, f of c times x, well, if c is between 0 and 1, this is going to be a horizontal stretch. And if c is greater than 1, it's going to be a horizontal compression. And so really one thing I want to point out that I haven't really said so far is that vertical changes, they're going to happen to the outputs of our function, right? Because the output values describe the vertical positions of all the points. So really these are going to be transformations to the function, to f of x. And horizontal transformations are going to correspond to transformations to the input, transformations to x. And as we saw in the last example and earlier on in this video, these two cases where we're adding some quantity to our input or multiplying some quantity to our input, they're sort of going to do the opposite of what you might expect them to do in this function. It's hard to sort of remember everything, but maybe that'll help. So we'll sort of apply an opposite idea to what you might expect. Right, so adding to the input does not shift our graph to the right, it shifts our graph to the left. Multiplying by some number larger than 1 to our input is not going to stretch it, it's going to actually compress it.